Hey everyone, my name is Parnita Rahi. I'm a principal PM lead within the AI frameworks team within Azure. And today, along with Savita Mittal and Pratik Rao, I'll be walking you through how you can build foundation models using Azure Container for PyTorch and Azure ML. A quick overview on the AI landscape. There's so much game changing stuff that's happening around us. And we are at a turning point moment in the AI journey where AI in generative and other form offers unusually large set of capabilities like text summarization, chatbot, search, and code generation. And we're getting started on this journey. And this landscape is now synonymous with massive amount of data and complex models. Managing complex data is not an easy task, especially under the time constraints imposed by discovery deadlines. So, for example, training time depends now on the complexity of the model that you select. And GPT-2 was over 100 times smaller than GPT-3. GPT-3 has 175 billion parameters and was trained on 570 gigabytes of text. GPT-4 is an even more complex model, and so is the case with a lot of open source LLM models that's available on Hugging Face. So, the right technology can make the model development process faster, easier, and less costly for your organization, and we'll show you how. In this talk, we'll focus on how organizations, data scientists, and ML experts can now use Azure to build their model development stack. So, if you're curious about how do I train state of the art models, which is applicable to my organization, we'll cover how pre-built environments built especially for PyTorch workloads. We'll also cover how you can deploy your large models in production and easily create online endpoints in Azure ML. And three, given compute cost is the new currency, how best you can optimize inferencing with ONNX. This is a quick overview of how PyTorch works on Azure. And so at the bottom layer, you have the best-in-class GPUs that's available on Azure, like the NVIDIA A100s and V100s. On top of that, there are three training methodologies that you could use either through SDK or Azure ML CLI or Azure ML UI or the Studio option. And through it, we now offer the like comprehensive training framework built using a curated environment called Azure Container for PyTorch, which includes within it technology that most researchers, scientists, etc., would need to build or train their models. So, for example, it has the latest versions of PyTorch, Python, the OS, Ubuntu, the drivers like CUDA or Rockham, and then it also combines on top optimization technologies that are required for faster training, like ONNX Runtime, DeepSpeed, and more. And so once you access Azure ML, you can now use these pre-built environment, and then on top of it, apply your base. Once you have your base image, you can apply your scripts and compute targets and create your training jobs. And using that, you can build your models and then also deploy it after converting it into ONNX across platform and any kind of hardware that you choose. So, what is Azure Container for PyTorch or ACPT? It's a curated environment for your large training workloads, which helps reduce preparation costs and provides faster deployment times. And this software stack is up to date with newest available and compatible versions of training software for ease of use. We release these images pretty much on a monthly cadence, so you have the latest version of PyTorch or Python or CUDA all in one place for a quick training setup. And these curated environments have been validated on a large set of Microsoft 1P or internal models. And it also includes Microsoft open source training optimization libraries like ONNX Runtime and DeepSpeed, which can, when combined or composed together, can give you speed ups of 54% to 163% over regular PyTorch workloads. Um, additionally, it is natively integrated within Azure, which means you can use like monitor your training jobs, you can create deployments, and you can also use the Azure customer support for any questions that you may have. Some of the latest technologies that we added in the ACPT curated environment or Azure Container for PyTorch. One of them is PyTorch 2.0, which was recently released. It is accelerated version of PyTorch, and having Torch compile is the main API for PyTorch 2.0, which wraps your model and returns a compiled model, and it's fully additive. So it has a bunch of enhancements that can give you that can help generate performant code, and also it helps hide a lot of the low level hardware details. So now with the Azure Container for PyTorch, you can easily include PyTorch 2.0 and earlier versions with ACPT in your training jobs. And we also include DeepSpeed, which is an open source deep learning optimization software that provides 10x faster training and is 6x cheaper to train and inference both dense or sparse models with billions or trillions of parameter. And you can easily use DeepSpeed with your PyTorch model using ACPT with just a few lines of code change, which both Pratik and Savita will show you how. Um, and then we also have ONNX Runtime. ONNX Runtime is a cross-platform machine learning model accelerator with a flexible interface to integrate hardware-specific libraries. With ONNX Runtime or ORT, you can train in one framework and easily transfer to another for inference. Using the ORT module class wrapper, ONNX Runtime for PyTorch runs the forward and backward passes of the training script using an optimized, automatically exported ONNX computation graph. ORT training uses the same graph optimizations as ORT inferencing, allowing for model training acceleration. And you can easily embed this within your training jobs with a single line of code, wrapping your model with the ORT module function. And similarly, for inference, you can also create an ORT inference session and provide your model path to use the inference optimization capabilities. The charts here show you some of the performance improvements on ONNX Runtime with ACPT. So on the left, you will see against PyTorch 1.14, when DeepSpeed and ORT are composed, we can see around 39 to 130% improvement in or improvement in throughput. And then on the right, again, it's comparing against PyTorch 2.0 with ORT 1.14 and DeepSpeed. And again, when you see the green line here, a DS plus ORT provides significant gains in terms of the throughput or samples per second, as when compared to both PyTorch 2.0 in eager mode and Torch compile. We also recently added Nebula to our Azure Container for PyTorch. Nebula is a checkpointing capability that helps speed and reduce cost. And this can reduce checkpoint times from hours to seconds, like from 95% to 99.9% of time. And it offers a simple way to monitor and view checkpoint life cycles. It is now also only available in the Azure Container for PyTorch on Azure ML. So, in the coming up section, Savita and Pratik will walk you through one training steps. So, how you can use the Azure Container for PyTorch or the curated environment, how you can create custom environment using ACPT or Azure Container for PyTorch, and how you can easily use DeepSpeed, Nebula, checkpointing, and ONNX Runtime Accelerator for improving the efficiency and efficiency for memory and compute. We will also then show you how to evaluate your model. So you will show you how you can register your model, how you can use pre-built fine-tuning model evaluation capabilities within Azure ML, and then also how you can register your ONNX model for interoperability across platforms. And then inference, we'll also talk about how to create an online endpoint, how to deploy scoring files, and how to invoke the endpoint to score. So now over to Savita and Pratik.
Hi, my name is Savita Mittal, and I work for Azure Machine Learning team at Microsoft and mostly focus on deep learning large language model training.
And hello, my name is Pratik Rao. I work on the ONNX Runtime team, also at Microsoft, and we focus on optimizing both large language models and vision models for production workloads.
Okay, so in this demo, we'll be fine-tuning T5 model with optimizations for summarization task, where given a large article, model will predict the summary. So if you're not familiar, T5 is an NLP model based on text-to-text framework and is used for tasks like language translation, linguistic acceptability, sentence similarity, and document summarization. So there are multiple variants of T5 model. We'll be using T5 small, which is 60 million parameter model. We'll cover mainly four concepts: training a model with managed experience with Azure Machine Learning, leverage out-of-the-box ACPT environment, which comes with pre-installed accelerators like DeepSpeed, ONNX Runtime, Nebula, etc. And then third, evaluate model using model evaluation component for computing the metrics. And then finally, operationalizing the model leveraging ONNX Runtime inference. So let's get started. So there are a few prerequisites that you would need. First is the Azure ML workspace. So if you can create Azure ML workspace on the Azure portal. If you go to the portal.azure.com, click on create a resource, and you can search for Azure Machine Learning. And you select the Azure Machine Learning workspace. Hit create. You can select your subscription resource group. If you already have existing resource group, you can use that, or you can create new, and then workspace name and storage account, key vault information, and hit review and create. So we have already created a workspace here. It's AML T5 demo workspace. And let's hit launch studio. So this is ML Studio. The next step we need to do is create a compute instance. You can click on the compute and create new instance. You can use CPU VM type and use standard DS12 or even DS3 would work to create the compute. So we have compute instance created, AML T5 demo CI. Now let's open the notebook. Now what we need is the T5 fine-tune model code. Right. To get the T5 fine-tune model, you can go to the ONNX Runtime Training Examples GitHub repository. We have published T5 model here. So you can git clone the repository and download T5 model code and upload it to the notebooks here, just like we did here. So let's open notebook train summarization. First step we're going to do is install prerequisites. So these are required to use Azure Machine Learning resources and managed experience from simple job running locally to complex job on local compute or remote compute. So once we have the Azure ML libraries installed, let's connect to our workspace that we created earlier. So Workspace is a top-level resource and provides a centralized place to work with all artifacts, whether it's a run or an environment or model. And this will provide us with the ML client handle to the workspace. And you can notice here the workspace name that we created earlier, it's AML T5 demo workspace. Now that we got a handle to our workspace, let's get compute resource. So Azure Machine Learning needs a compute resource to run a job. This resource can be single or multi-node machines. So we'll provision standard ND40 RSV2 SKU, which is 40 cores with 8 GPUs and InfiniBand enabled. InfiniBand provides higher node communication bandwidth with Mellanox drivers. So these GPUs are powered by NVIDIA Tesla P40 and specifically designed for deep learning workloads to get excellent performance and almost linear scaling. All right, so we got our workspace, we got our compute. Now the next we need is the curated environment. So let's create a curated environment using Docker context where all required packages are installed to run a fine-tuning job. So let's run this cell. So while this cell is running, let's look at the Docker context. So if you click on the under environment context, you'll see the Docker file. So you'll notice here we're using ACPT PyTorch 2.0 with CUDA 11.7 image, which is a curated image provided out of the box by Microsoft and includes latest PyTorch 2.0 with several accelerators like DeepSpeed, ONNX Runtime, Nebula checkpointing to speed up your training and inference. Since we need some additional packages to run our training job, like transformer, dataset, we added to the existing image and creating a custom environment. So now let's go back to our notebook. You can also go to the Studio UI to look at the environment. So you can see this is the environment that we are creating here. And you can look at the Docker context. And this is the same Docker context. So now what next? So we got workspace, we got compute, we got environment. Now let's get the data we want our model to be fine-tuned for. We'll be fine-tuning our model with CNN Daily Mail dataset, which is an open source dataset from Hugging Face. It's an English language dataset containing just over 300,000 unique new articles written by journalists at CNN and the Daily Mail. So let's see the sample rows. So you can see here it has 3 columns: articles, highlights, and ID. So given a large article, the model will predict the summary or the highlight. And this is the training data set. All right. So now that we have all resources needed for Azure ML are available to run a training job, let's submit the fine-tune for T5 model. Let's run this. Okay, few of the parameters that you will notice here are the model name, which is going to be T5 small model, ORT, ONNX Runtime, DeepSpeed as the accelerator, and then Nebula checkpointing. And we are running for single epoch with 10 samples of training data. And now, Pratik, do you want to walk through the script?
Yeah, absolutely. So how do you actually go about creating a fine-tuning script to fine-tune the T5 model on the summarization task? Well, luckily, Hugging Face on their repository provides an example script. So what we've done is we've started with the vanilla PyTorch Hugging Face transformer script, copied it into our notebook here, and I'm going to briefly run through the few line changes we made to enable ONNX Runtime to optimize your training workload. So the first one I would like to point out is right there on the screen. You can see lines 21 and 22. We have the optimum imports for ONNX Runtime. ONNX Runtime is actually integrated natively into the Optimum repository hosted by Hugging Face. So all of the examples that work on the Hugging Face hub will work out of box via Optimum. The next line that I would like to highlight is line 305. Line 305 showcases how to use the ONNX Runtime sequence-to-sequence training arguments. So there's a small change here where ONNX Runtime has some additional arguments that can be passed in. For example, we have our own AtomW optimizer that provides memory savings as well as runtime savings. So for our task here, we just have to adjust the training arguments parameter to take in the ORT sequence-to-sequence training arguments instead of just the vanilla Hugging Face training arguments. So the next line that I would like to highlight is line 580. Line 580 in this script demonstrates the usage of ORT trainer, or in this case, ORT sequence to sequence trainer. And what this does is under the hood, it'll wrap your model in our ONNX Runtime ORT module, and that comes with all of the necessary additions for exporting it to a graph format, using that graph format to generate compiled nodes, and thus seeing speed up on your training jobs. Last but not least, on lines 607 and 609, we have the export step where you then convert your fine-tuned model to an inferencing model to use in later steps when you want to set up an online endpoint or really anything involving pure inference after fine-tuning. So this step is important because here we see the connection between how we're fine-tuning with ONNX Runtime and feeding that into inferencing with ONNX Runtime. And later in the demo, we'll showcase the speedups that you can see on the inference side as well as the training side. We have also on line 603, 604, and 605 some helpful links for generating an ONNX graph based on any general model architecture that you would like to fine-tune. Thanks. Back to you, Savita.
All right, thanks, Prateek. Now let's look at our job. All right, so at the end of the cell, you'll see a URL. Let's open that. You can see the job is running. So in the job, you can see all our code, fine-tuning code is uploaded to the artifact store here. And you can also debug and monitor while the job is running. You can connect to the Jupyter Lab, VS Code, and TensorBoard. The job is running. We have published best practices for large-scale training from Microsoft. So if you go to the aka.ms/AzureML-large scale, so you'll notice here that we have all the optimizations you could leverage to optimize for compute and memory efficiency, whether it's data loading. You can have a large file versus large number of small files, how to optimize. You can see the environment for ACPT. And then for training, there are multiple accelerators you can see on DeepSpeed, ONNX Runtime, the compute cluster with InfiniBand. And we have also published the training sample codes for BERT pre-train as well as Bloom pre-train. Now let's go back and look at our run. Looks like it's completed the status. And if you look at the output and logs, you'll see the PyTorch model, the ONNX model, as well as the ML flow model. Let's go back to the notebook. So here we are showing you the result with 300% improvement for fine-tuning job. To compare, we ran 2 fine-tuned jobs of T5 model with 100 epochs without any accelerator and with ORT and DeepSpeed accelerator. Training time is reduced from 33 hours to 10 hours with 300% improvement. Similarly, the train samples per second is 241, whereas with the accelerator, it's 744 samples trained in a second. Now we got our model. Let's register our model. So this will track lineage between the fine-tuned model and the fine-tuning job. All right, so we got our model registered. Let's evaluate how good our model is. To evaluate the performance, we will use standard Rouge metrics with a small test data. Here we are using an inbuilt reusable component offered by Microsoft, which can evaluate the model given the task type. These pre-built components are published to asset registry. In line 22, we're pulling the component called model evaluation pipeline from registry. And in line 29, there's a function evaluation pipeline which leverages this component. And all we need to do is pass model file, task as the text summarization, input, and label columns. You can also specify the metrics you would like to evaluate the model on. Since model evaluation can take a bit of time, I've gone ahead and run it ahead of time and captured the results here. So you can see here, it shows the pipeline graph of model evaluation and the metrics for Rouge 1, 2, large, and large sum metric. Now to summarize, till now we have fine-tuned a T5 model using custom environment of ACPT with Azure Machine Learning and evaluated our model performance. Now, Prateek, do you want to walk through the operationalizing of model?
All right, thank you, Savita. Now that we have a fine-tuned model that we've determined meets our accuracy metrics, how do you actually productionize that model, use it in a way that users can access it from anywhere in the world based on some sort of application endpoint? Well, if we look at the first thing here, which is a picture of the Beam Search ONNX graph, you can see the required inputs for our ONNX model. And at the very left of that image, you can see the input IDs. The input IDs are the tokenized outputs of the input article that the user will be feeding to you. So if you scroll down a little bit, we can take a look at the two main functions that are required for any sort of web application leveraging machine learning inferencing. The first one is loading the model or any ancillary parts that are required, and this only needs to be done once on startup. So we have here our init function that defines both our ONNX Runtime session object and the tokenizer. So the ONNX Runtime session object is a inferencing engine that takes in an ONNX file, which again is a graph representation of a PyTorch model, puts it into the inference session object and allows you to set whatever providers that you have available. So we have here set the CPU execution provider on line 19. You can replace that with a CUDA execution provider if you have an NVIDIA CUDA device. You can also include both of those terms in that list of providers, and what ONNX Runtime Inference Session will do is it'll go in and it'll find whatever the best architecture that's available on your machine is, and it'll run it via that architecture, that backend EP. So you have one script that you can run on any compute target, and it'll just find the best execution provider to run given what was in the providers list. And on line 21, you can see we also load the Hugging Face tokenizer that converts the raw article to tokens to feed into your large language model. So these are the two things that need to be done on startup of the machine only once. Next, I would like to talk about the run function. So if you scroll down a little bit more, the run function here we can see takes in as input your article. It parses it out from the JSON that is inputted as could be the body of an HTTP request. We generate our ORT inputs variable as so with the input IDs as well as all of the constants that are required for the T5 beam search algorithm. On line 40, we actually utilize our ONNX Runtime Inference Session object. So we pass in our ORT inputs and we get back out the inferenced output. And lastly, on line 42, we pass that output to the decoder to get our human readable summarization. Savita, you can go ahead and run this cell. And then if we scroll down, one thing I want to quickly highlight while this is running is this test function here. Line 61 to 66, what we're doing is we're actually feeding the our fake API endpoint 10 HTTP requests, and then we're averaging the time to get a reliable metric of how long the inferencing took. So here we can see that the inferencing time is about 0.38 or otherwise 0.4 seconds per inference. If we scroll down to the next cell, you can go ahead and run it. And I would like to highlight in the init function on line 25, instead of having an ONNX Runtime Inference Session object, here we're just loading the plain model and we're going to perform the forward pass on the model as you would in, say, a vanilla PyTorch inferencing scenario. So Savita, you can scroll down a little more. We're still sending 10 requests and averaging it across those 10 requests. And you can see that the runtime has ballooned to about 0.778 or 0.8. So that's about 2 times speed up you get with just a couple lines of changing to utilize ONNX Runtime Inference Session. So To summarize again, we've gone all the way from creating your ACPT environment, fine-tuning a model, evaluating that model to make sure it meets your accuracy requirements, and then finally leveraging that model in an inferencing scenario. We hope that you take some time to utilize all these technologies to really speed up your inference workloads when you're utilizing large language models. Thank you.
Thank you.